All right, everyone. How are we doing today? All right. Wonderful. Okay. So let's get started here today. There is one thing that I want to mention, and I will send an announcement if this ends up going through. Um, I think we're going to change rooms for this class, uh, mostly so I don't have to deal with this. But I think maybe it'll give you all a little bit more room too. We'll see how it works out. Um, But if that happens, what I'll do is I will post a Blackboard announcement and tell it to email everybody. So you should get a notification about that. So I don't know if it'll happen before Friday, but it might. So anyway, we'll maybe do that. And then otherwise, I've updated what's posted in Blackboard for a couple of things. The quiz for this week's already posted, as well as the updated table of contents page for the notes. Oops, that's not the wrong right key. All right. So there's the 12.5. The 12.5 and 13.1 were already posted if you had looked at this already, but 12.6 is up there now as well. So you can check those out. I'll be referring to some of this today as well. Okay. So section 12.6 is about more kinds of graphs that appear in 3D space. Okay. One of the main things that we have to adjust in our understanding of the plots that we're looking at is that they don't work exactly the same way as they did in two-dimensional situations. In 2D, when we would have our plots, the idea is that we would tend to think of them as being structured like this. Okay? We have an independent variable and a dependent variable, and we would have whatever it was our curve look like. Okay? And this is how we would organize the information. Okay? There was an independent variable that was associated with one of our axes, and there's a dependent variable that's associated with the other axis, and we go from there. Okay? Now, we've been graphing different types of functions so far this week, including talking about space curves. So we have our space curve, we have our XYZ axes, and the makeup of what gets graphed here is this. Okay? Our independent variable is hidden. Okay? We have some curve that loops through space here, and there is an orientation to this. Okay? And the idea is that the arrow indicates the direction of how the curve is drawn for increasing t. Okay? So you saw that when I drew the curve, I drew it by tracing it out that way. Okay? That's how it would be drawn in real time if we were looking at the points and cataloging them as t increased from on some range. Or on some interval, excuse me. Should be more careful about that. Okay? This is how it works for graphs. Okay? for surfaces, there are two different ways that we can think about how things are put together. And for the most part, we don't use the function version in what we're discussing for this section. Okay. Another situation that we can have, and this is a type of thing that we will see, but it is not what we're going to be discussing primarily for the purposes of this section. Okay. This would be the picture that looks kind of like the way that we're used to thinking about functions in the normal sense. Okay, we have independent variables and they contribute to a dependent variable. So x and y are both independent variables for this purpose. And f of x or z equals f of xy is a function of those two variables. So if we were to make the surface that is associated with this, what we would expect okay, and I'm not going to try to get too fancy with the drawing here. All right. Okay, it's got some valleys and some peaks to it. All right. But the idea is that the way that this is drawn is that it passes the vertical line test because it's a function, right? Each set of inputs can result in one and only one output. Okay. All right. Now, this is a valid way to think about a surface in 3D, but it is far from the only type of surface that can be defined. Okay. Another thing that we can do is talk about a surface that is defined by just some equation, all right? And there's nothing that says that that equation has to be a function. Just like in 2D space, I could write down this equation. It's not a function, okay? So what we're going to be working with are surfaces that are given by an equation. For this section, a particular class of equations, those that are quadratic in nature. Okay? So let's get started here. Okay, I'm going to write out okay. That is the general form for the equation of a quadratic in 3D. Okay, now it looks like how we would write these things out in 2D. That's what I would have if I had a quadratic in just single variable, right? The issue is that we have three variables. Okay, so unlike the second case where we looked at where the thing could be a function where z depended on x and y, that's not necessarily the case here, right? Because z can be squared too. All right, so we don't have that necessarily being a function. So for the purposes of this equation and determining the level sets, or determining what the surface looks like, one of the techniques that we will use is looking at the level sets. Is it depends on all three variables. Okay, it's not one, it's not two, it's all three. And when we make a visual representation of this, our plot, our picture, it's not a situation where two of the variables give us the third or something like that. All three of the variables are effectively independent. Okay, it's just a matter of whether or not they just represent the locus of solutions is the technical term, but the set of points that satisfy the equation for the quadratic that make this true for particular values of a, b, c, d, e, f, g, h, I, j. Okay? All right. So what we want to do, oops, sorry, I skipped a step here. Sorry about that. Okay, we want to consider this quadratic equation. This is the equation that gives us our expression, and what we want to do is try to figure out what does the plot of this look like. Okay? Now, one of the things that we can do is employ a technique known as traces, as it's referred to in your textbook, or as I called it a couple minutes ago, using level sets. Okay? So we don't know how to deal with 3D functions. Okay? We don't have an intuition for that. All right? And there's no point in trying to draw something that complicated until we have developed a pretty extensive set of examples and understanding. Okay? But what we can do is simplify the problem. Okay? So I can imagine that this is going to be some set. Okay? I have no clue what the surface looks like for this expression. All right? But I can say the only thing I'm going to worry about right now is the part that intersects the plane z equals 2. Okay, I'm just going to pick a value for z and set z equal to 2. And then I will look at the equation with z equal to 2. What I can do is I can then graph what that would look like. Okay, and then I start picking different values for z. And if I pick enough different values for z, what I can do is build up a set of sketches that will allow me to figure out potentially what this thing looks like. Okay? So I'm more or less taking cross sections of the surface at different heights. And if I have enough cross sections, then I can infer what the surface looks like. Okay. This, by the way, is how we do things like MRIs. Okay. They put you in the big box, and they have a machine that goes through, and they're not scanning your whole brain at one time. What they're doing is they're scanning on a plane, right? And then they take multiple planar scans and then try to use that to reconstruct the 3D image. Okay? It's part of a general technique known as tomography. Okay? Tomography is any time where you take slices like this and then try to construct a more complete picture. Okay. So this is what we're doing. So we can set z equal to 2. That gives us a different version of the equation here. Like so, right? 2 squared is 4. Okay. And then so what this tells us is that at the height z equals 2, what's the only solution for that equation? What? It would have to be 0, right? Okay. Because that's the only way to get something squared to equal negative something else squared. Okay. So this tells us where the top of this shape is, it turns out. Okay. It reduces to a point at, so this is either the top or bottom if we're looking at it in terms of the z-axis, because the whole surface reduces to a point. Okay. Now, wouldn't the same thing happen if I set z equal to negative 2? Okay. So all right. So we didn't glean a ton of information from that particular choice of the value. Okay. But it does give us the edges of the shape in some sense, right? So we have what must be a top or a bottom, right? Or the top and the bottom, because we were able to find two values that trapped it. Okay. Now, we could also select z equals 0. And if we do that, we're going to get x squared plus y squared over 9 equals 1. And what is this the equation of? It's not quite a circle. It's an ellipse, right? Okay. The fact that there's something in the denominator is what makes it an ellipse as opposed to a circle. Okay. So the real form of this equation, if we're thinking about it as an ellipse, would be this. Okay. And the values that are squared in the denominator represent the lengths of the semi-minor and semi-major axes for the ellipse. Okay, so this tells us that on the xy plane, the ellipse looks like this. Right? That pesky chapter 10 from Calc 2 that nobody wants to remember. That one. Anyway. Okay, so this tells us our shape here. All right. If we picked other heights, we would get other, with harder to compute values, slices that would also be ellipsoidal. Okay. And taken all together, this information allows us to make a sketch for this particular quadratic. I will do my best. Okay. But it is an ellipsoid. Okay, we know that that point is 0, 0, 2, and this point is 0, 0, negative 2. We know that this point over here is 1, 0, 0. We know that this point up here is 0, 3, 0. And this one is 0, 0, or sorry, 0, negative 3, 0. Okay, so for this one, fairly easy to figure out what's going on. Okay, but for other shapes, we might have to draw more of these level sets in order to get an idea of how things are put together. Okay? Yes. So part of it's guessing. Okay, sorry. The for those of you in the chat, the question is, how did I know which values of z to pick? Part of it is looking at this term here, choosing values that would be bigger than 2 might cause problems with this equation. It turns out that if I would have chosen values that were larger than 2, I would have gotten equations that don't have, I wouldn't have been able to solve the problem. Okay, so if I had chosen, say, z equals 3 here, I get this equation, right? All right, I would have gotten a negative number on the other side of the equation, so it would have been an inconsistent thing, so there's no x and y that would make that true. Okay, as for other numbers, you often pick 0 because it's easy, unless there's something that's preventing you from picking 0. And then from there, it's just a matter of you make a couple of guesses, and based on there's always going to be 1 or 2 values that are easy to pick that you can get a little bit of information from, and then from there you choose other values to fill in the gaps. Yes. You can choose. The question is, do you have to pick values for z, or can you choose to choose values for x or y? You can choose anything that you'd like. Okay. So the whole point is that we have, as seen in this picture here, just numbers that we're choosing for planes that we're using to slice the surface with. Okay. There's nothing wrong with me deciding that I want to cut it this way. Okay, or cut it this way. is supposed to be along that with choosing values for x, but that's harder to see. No, we are trying to choose. Okay, so the question was, are we trying to make to get 0 somehow? We can't guarantee that that's going to happen. The reason that it happened in this particular case was because we have a surface that terminated at a point. All right. There are many examples of surfaces that are infinite, and so it's impossible to choose a cutting plane that gives something that tells you what the boundaries of the figure are. Okay, so this first one was a special case. Let's keep working and do some other examples. Okay. Look at a different type of surface. We have z equals y squared minus x squared. Okay. So what we're going to do is we are going to do the traces for all 3 variables. Okay. And so this gives us z equals y squared minus k squared. This gives us z equals k squared minus x squared. And then this one gives us k equals y squared minus x squared. Okay. We have x and y here. We'll do x and z and yz for the axes labels here. Okay. It doesn't matter how you label the axes, it's just a matter of making sure that when you put the pictures together, you organize things correctly. Okay. So what we want to do is go through and analyze this. Now, when we reduce it to this type of expression, okay, you should have a little bit more familiarity with this and be able to guess based on what these equations look like most of the time what the graph looks like. Okay, so what does the graph of z equals y squared minus k squared look like? Okay, why would it be a hyperbola? Okay. All right. So the person who responded to my question about hyperbolas is looking at this minus sign. Okay. And if you have the difference of quadratic variable terms, then you have a hyperbola. That's correct. Okay. The thing in this case, though, is that k is not a variable. For a particular trace, k is a fixed number. Okay. So this is y squared minus a constant. All right. So that's why we use k, because we have to we want to remember that hard C sound or that hard K sound is it's a stand-in for some fixed but arbitrary constant. So because it's y squared minus a number, this thing is actually a parabola. Okay? And what that K value does is tells us where we cross the z-axis. Okay? Because what this actually looks like in variables that you're probably more familiar with would be this, if we were writing it as an xy equation. Okay, that's a parabola that opens up that crosses the axis at C. Or sorry, minus C. So shifted, sorry, it crosses at C. It's, or negative. I need to stop talking. I got my minus signs mixed up. Anyway, okay, y'all get the point. So what that allows us to do is sketch a few of these. This is K equals 0. That would be K equals plus or minus 1. Down further, we would have K plus or minus 2 because it's squared, so it's harder to write out. I can be cute and do this. Okay, so that's what that looks like. All right. Now, having done one of these, looking at this equation, we see that it's the same thing except it opens down, right? Okay, and then we do need to be a little bit more careful about how these are drawn because, of course, the the farther we go, it narrows, right? In terms of the way that the parabola grows. None of those lines cross, right? But it does. The lines do bunch up. Okay. All right. Now, what about this final expression here? All right, in the back. What kind of shape is this? That one's a hyperbola. That's right. Okay. The reason it's a hyperbola is because we have this minus sign here between variables that are quadratic, right? Y squared and x squared are both variables and they're both squared. So if I take the difference, it means I'm going to have a hyperbola. And because there aren't any constants here, it is a very symmetric hyperbola. So we get this. And then there is also a special case when k equals 0. Okay. So this one is for 1. The straight lines are for 0. And then we have -1 here. So 1 basically are the vertical, the ones that open up and down, and -1s are the ones that open side to side. Okay. The reason that works that way is because if I set k equal to 1, I get this expression. If I set k equal to -1, I get this expression, which is the same except multiplied by -1, which is why the orientation changes. Okay. Yes. So if I'm fixing x, I need the other two. And then which one I write as z and which one I write as y doesn't matter as long as I draw the picture correctly. Okay. All right. Okay. So now we want to convert here to using this information to help us draw the picture. Okay. So I'm going to do my best to try to help us see what these sketches would look like and how we would be able to combine them in a useful way. All right. So we have x and y and z, and our level sets here are in x. Okay. So our cutting planes are sort of parallel with the screen. All right. And they represent the different values for x equals k are different slices that are parallel to the screen. So at 0, we get this parabola. Okay. And I'll note that it's touching here. Okay. At 1, we get a different parabola that's closer to us that touches below the x-axis, right? Because it touches down at z equals -1. Okay, and then we get another narrower parabola that's closer to us. So each picture that I have drawn is closer to us. All right. The perspective makes it really hard. I know. I'm sorry. Okay. We can do something similar with this plot here. Okay. This one turned sideways is going to be a little bit easier to see what it is we're supposed to see. Okay. Here, our slices are this direction, parallel to the xz plane. Okay. At different values for y. Okay. And so here we have k equals 0, k equals 1, k equals -1. All right. So these are along in the y direction is where these things are set up. And then lastly, we have the ones in the z direction. Okay. So these sit flat in the plane. Level with the floor. And look like this. Okay. Now, taking all this information and synthesizing it into a single thing. a little tricky. But it looks like this. Okay. Okay. It has a saddle shape to it. Okay. So here it has that downwards opening parabola bent to it, right? This is one of those shapes that it's kind of hard to deal with in terms of especially sketching. Does this make sense? Okay. The main idea here is that based on the pictures that we have drawn, we need to be able to put all this information together, right? Okay. Here, I have those parabolas that are on the shape here, right? Okay. In the x direction, that is how this shape is changing. Okay. Here, I have those parabolas that are opening down. Okay. And also, the hyperbolas. Okay. All of those things, at least to the limits of my poor drawing ability, okay, are present in the sketch. Right? Now, from you all, I don't expect perfection. All right. This is about all I can reasonably ask for you to do. Okay. Is to come up with a decent set of traces. Okay. The traces should be the part that makes sense, right? Like, you know how to do those. I know because you had to take Calc 2 to get in here. All right. That you can graph quadratics in 2D. Okay. And then we put those together to try to come up with some sketch for the 3D shape. Now, fortunately for us, there's a classification system that we can employ to guide us in this process. All right. There are only so many types of quadratic surfaces that might be out there, right? So if we take a look at the online notes, okay, there's a little bit of discussion of implicit functions, which is kind of similar to what I had mentioned at the beginning, different take on it. Okay. We're familiar with quadratic curves, but there's a little bit of information here to remind everyone of what's going on. And then we have kind of a special case for quadratics that we had discussed earlier, which are cylinders. Okay, this came up in one of the earlier sections in chapter 12. Okay, this is quadratic because both of the variables are involved in quadratic, but we have a free variable. Okay, for cylinders, either x, y, or z is missing, depending on what the orientation of the cylinder is. So here we have z missing, so it's a vertical cylinder. Okay, and then you can have one that points parallel to the X or Y axis as well. Or, of course, you can also have one that points along any axis, but that would make the equation a little bit more complicated. Okay. There's also infinite other parabolic sheets like this, okay, where we have a missing variable, either x, y, or z, and then only one of the remaining two variables is squared. Okay, so this picture here is z equals y squared. Okay, x is not specified, so it's a free parameter, so you have a parabola that's copied for every value of x. Just like a cylinder is a circle that is copied for every value of the missing variable. Okay, and then you can also have, of course, ellipsoid or ellipses or other sorts of shapes that are done in the same way as a cylinder, right? You could have an ellipsoidal cylinder. It would just be the equation of ellipse that's graphed in 3D where one of the variables is missing. Same deal. Okay. All right. Now, in the discussion here, there are some pictures to help guide you that are made on a website called GeoGebra that you can investigate. One of the pictures is broken. I'll have to fix that. And one of the things to pay attention to, and this goes along with a comment that was made earlier when we were trying to figure out what one of our 2D equations looked like, is for our big, long expression in this form, you want to pay attention to the SIGNs on the quadratic terms. Okay, so the x squared, y squared, z squared terms, if the coefficients on those are negative, depending on how many negative coefficients you have, that will tell you what sort of gross shape the quadratic surface is. Okay? So if we look at this, all right, we get parabolas and stuff, okay, or parabolic cylinders if only one of the variables is squared. Okay, that's where the parabola shapes come from. We will have an ellipsoid if all three of the x squared, y squared, z squared terms are positive. Okay, that forces the shape to close in on itself and give us an ellipsoid, which is what we had in our first example in class. Okay. In this shape, we have another type of parabola sort of thing. You'll notice that's because the z is not squared here. Okay, so it's missing z squared, so it's parabolic in the x and y directions, and then opens towards z. Okay, so it opens in the direction that z is pointing, either up or down based on the signs in the problem, and then the shapes that we get associated with the variables x and y are both parabolic. For hyperboloids, one minus sign. Okay, and the way that these are going to work is that you can have hyperboloids with one sheet, or you can have hyperboloids with two sheets. Okay, and it has to do with the way that the minus signs are set up. And what this value is here on the other side. Okay, so this is all gone through, and there's several pictures of this. All right, but basically what you can have is you can have a hyperboloid that looks like a nuclear cooling tower, okay, that doesn't have the middle that cinches in on itself all the way, okay? If you have precise conditions, the middle of that nuclear tower shape cinches in exactly to a point. That's when you get a cone. okay? And then if the value, the constant value that shows up in this equation is negative, then it cinches off earlier than exactly 1 point. And that's when you get the two half shapes, and you have two sheets in your hyperboloid. Okay, so follow through for the examples for here. Okay, and then I wanted to go through and do the practical bit of drawing the traces and going through that process with everybody. And then you can read through this and read through the pictures, and then make sure that you're counting the number of minus signs correctly in order to build up everything else. Okay, enjoy your day, everybody, and I will see you next time.